chiral superfields. Chiral superfields were fields that obeyed del bar alpha, or maybe alpha dot, phi is equal to 0. Okay. Remember, this d bar was the derivative that commuted with the supercharge. So this was a supersymmetrically covariant condition you could put, and any such field was a function of x mu minus, what is it, x mu x mu plus I theta sigma mu theta bar. Okay, this we sometimes call y mu, and it can also be a function of theta. Okay, so all such fields were functions of theta, and this y mu, where y was this linear combination. I'm sorry, this board keeps. Anyway, theta and this linear combination of x and bilinears in theta. And then we performed, so then we said that the most general chiral superfield had the form phi was equal to, let's use Wesson Backer notation, was equal to A plus, well, it was a field plus theta times a fermion plus theta theta bar times a boson, where the fermion, the original scalar field, the fermions, and the last boson were all functions of y. Okay, and then expanding those fields in functions to get functions of theta and theta bar, we found A plus square root 2 theta psi. This was the field that we started with, plus theta f. It would have been, it's this as a function of y's, and then we expanded the y's to get these additional terms, right? Plus square root 2 theta psi plus minus I by square root 2 theta theta del mu psi sigma mu theta bar plus theta theta. Oh, sorry. So the expansion of A was A plus I theta sigma mu theta bar del mu A plus 1 by 4 theta 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 bar box A. So that was just the expansion of the first term. Then there was the expansion of the second line, which was plus square root 2 theta psi minus I by square root 2 theta theta del mu psi sigma mu theta bar. That was the expansion of the second term. And then there was the expansion of the third term, but there was no expansion of the third term because f came with 2 thetas, so third theta kills it. So that was just theta 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 f. Okay, this was the general chiral superfield. Matter fields in our gauge theories will be chiral superfields. Excellent. Now, in addition, that's a disaster. What do we do about that? Let me see. How athletic can I be? Is there a, well, that's, there is a stake and there's a hook, but I think it will go beyond my abilities to scoop it up. Let me see. I think we need a probably. Let me see if I can anyway do it.
Yeah.
If I can go in the middle. You want to try?
No.
Well, this goes in the middle here. I mean,
No. It's to be flipped.
yeah, just one second. So, almost. This is a strange design. Thank you.
Opened, right?
I mean, maybe we can ask the office to open it if it's the only way.
Now I think we opened it. Yeah. We can. Oh, निकाल दो. इसको इधर लेके आओ.
ऐसे करना है इसको, शायद आ जाएगी हाथ में.
तो इसे उधर जाना पड़ेगा.
I'm so sorry. Oh, well done.
Great.
Thank you. Wonderful. I'll keep the book here. Okay, so this was the chiral superfield. The chiral superfields were going to be matter in our theories. Okay, then we also looked largely at, we looked only at U1 so far, and we looked at gauge bosons. Now gauge bosons were part of a vector superfield. Okay, a vector superfield, unlike a chiral superfield, was real. Chiral superfields are always complex. Vector superfield was real, and the important thing was that in the expansion of the vector superfield, there was a gauge boson. The gauge boson appeared in the term plus theta sigma mu theta bar v mu. So the theta theta bar term had a gauge boson. Okay. Now, this vector superfield is going to be our gauge field, and this v mu is going to be the is going to be the supersymmetric completion of the gauge field, and this v mu is going to be the actual gauge field. Now, we had this gauge invariance. So v goes to v plus phi minus I phi bar. Phi plus phi bar. This was a gauge invariance in our setup. Okay? And we showed that it was possible to use this gauge invariance to move to this so-called West Sumino gauge. Right? This West Sumino gauge was the gauge in which this V took the form theta sigma mu theta bar V mu plus I theta 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 bar lambda bar minus I theta bar theta lambda plus half theta 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 bar d. Okay, these are the physical fields in a gauge multiplet. Okay, this guy is the gauge boson, and these two are the gauginos, the fermionic partners of the gauge boson. D is an auxiliary field that will play a role similar to F for a chiral superfield. Integrating it, it will have no kinetic terms, and integrating it out will produce terms in the potential. Okay, all good. The last thing that we discussed about kinematics for this four-dimensional theory was that we constructed this field W alpha, which was d alpha d bar of V with a minus 1 by 4. Okay, so the way we wrote it was d alpha. Okay, now this field was a chiral superfield. That's clear because you act with d bar on it, you get 0 because there are 2 d bars. Okay, so we have a chiral superfield, and we talked about how the Lagrangian for the gauge boson, for the U1 gauge boson, took the form integral d2 theta w alpha w alpha. We evaluated that Lagrangian in components, and we found that this was integral, I mean, of course, there's d4x, which I hadn't written before, half d squared minus 1 by 4 v mu nu v mu nu minus I lambda del slash, okay, sigma mu del mu lambda bar. It's a slightly strange notation, but I'll see it. Okay, so the kinetic term for the gaugino, the kinetic term for the gauge boson, and D. Note we're looking at the pure theory of a U1 gauge field. So this theory is non-interacting, it's just quadratic. Okay, so far this is what we had. Was this clear? Any questions or comments about this? This is F mu nu. Right, so we got F mu nu, and then you see that F mu nu in supersymmetry is accompanied by a kinetic term for a scalar, for a spinner, and that spinner is what we call the gaugino. Okay, all good. So far this is all very nice, but we're sort of fooling around because we've only written down non-interacting theories. We wrote down, we had the possibility of interacting theories for these chiral superfields. I don't know if you remember, but we wrote down a Lagrangian which was d4 theta phi bar phi plus integral w of phi for any w plus hc. Standard kinetic term plus arbitrary potential term. And if we wanted to generalize that kinetic term to something more interesting but 2 derivative, we could write down any function of phi bar phi there. Right? So with the chiral superfields, we have the ability to write interacting theories. So far for this gauge boson, we've only written down a free theory. Now we've only written down a free theory because if you stick to 2 derivatives for a U1 gauge field, the only theory you can write down is free. It's just F mu nu, and that's supersymmetrization. But of course, you can get interactions by, even in U1 theories, by having U1 theories interacting with matter. Okay, so now the next thing we have to learn is to understand how to make interactions between these gauge bosons and the matter. Okay, and that's actually very easily accomplished. Please go.
There is a gauge symmetry in V, but there is none in this lambdas.
None in lambdas, because lambda is a neutral field.
It's like the psi.
It's like psi, it's true, it's sort of like psi, but psi could be psi, you mean up there? But psi, you see, is a matter field, it could be not gauge invariant, it could be charged. Whereas this guy here is the gauge boson in the same multiplet as a gauge field, sorry, the fermion in the same multiplet as a gauge field, therefore must be uncharged. Okay? The non-abelian version of it will be that this field will have to transform in the adjoint. But adjoint representation for U1 is uncharged. Okay? Therefore, it's gauge invariant. Okay? Whereas these guys, as you will see, could be charged and therefore would transform under gauge transformations. Is this clear? Okay, excellent. So now precisely to answer sort of Trakshu's questions, what we're going to try to do now is to try to understand how to give interactions to these, how to make the gauge bosons interact with the charged matter fields. So let's suppose that phi is taken to be a charged matter field of charge 1. Okay, for that charge 12, the generalization will be clear. Okay, And now we want to make a gauge invariant system. So you see, what we had here was that this V transforms like this, and if you remember, when V transformed like that, if phi started out as this phi here, maybe I'll call this a psi, because we'll leave phi for the charge scalar fields. Okay, so suppose psi started out as A plus blah blah blah. Okay, then the gauge boson part of A, V mu, went to V mu plus del mu A, maybe minus del mu A. You remember we discussed this last time. Okay, so you see that the first component of psi is the usual gauge parameter. Okay, the first component of this psi here is the usual gauge parameter, and V mu is the usual gauge field. So now what we want to do is to think of a chiral field, which is matter, which is charged under this gauge field. Okay, so how does this transform under gauge transformations? Well, it's sort of clear, right? Phi must transform like e to the power I psi phi. Right, because then the first component will transform. First component of phi will transform correctly under the first component of psi, and then everything else will follow by supersymmetry. Okay, I think that this, for this psi, they sometimes use the word they use lambda. I may change the psi to lambda to stick to Weissenberger in notation. But yeah, okay, I'm sorry, this guy is lambda. Let's call this lambda. Well, lambda is a chiral superfield. Okay, so what we want to do is to make interactions that are invariant under such transformations. Okay, but how do we make such an interaction? That's sort of clear. Suppose we take this phi bar phi, which was the kinetic term in the absence of gauging. Okay, suppose we take that thing and we upgrade it to let me get the sign right. Suppose we upgrade it to phi bar e to the power v times phi. Okay, now you see under this maybe I have my lambdas. My factors of I, just a minute. Yeah. And I want minus I lambda minus lambda bar. Okay. Okay. So I have I lambda here. Because of this, phi bar goes to e to the power minus I lambda phi bar. Lambda bar. Okay. So now if I put this in here and put in the transformation of V, which is this I lambda minus lambda bar, clearly the I lambdas cancel, the I lambda bars cancel, and we're good. Okay. So this guy here is a gauge invariant interaction. It's a gauge invariant kinetic term. This guy here is a gauge invariant kinetic term for the matter fields with the gauge bosons. This is the supersymmetric analog of minimal coupling. You see, remember, kinetic term, although it doesn't look like it from this point of view, kinetic term is a term with derivatives. Where did the derivatives come from?
Y to x.
Exactly, y to x, because in the expansion of y to x, we Taylor series expand, and that gives us derivatives. Okay, so this guy is the term with derivatives, and as we know, the way we make gauge boson charge matter fields interact with gauge fields is to replace all derivatives with covariant derivatives. Okay, so this is the analog of that. Okay, now this might actually seem really very strange, right? At first it might seem very strange because this v is like e to the power v. So it looks like some interaction that goes on forever. Okay? But if we work in West-Sumino gauge, if we work in West-Sumino gauge where v takes this form, the expansion starts with 2 thetas, with theta, theta bar, and therefore it can at most have v square. So that e to the power of v is actually 1 plus v square by 2 in this gauge. Okay? Now 1 plus v square by 2 is good, because we know that when we have scalar fields, we have interactions including a square, because d mu phi includes 2 a's. So we wanted something that was at least quadratic in gauge fields. Okay? So this term has exactly the right properties. Okay? And of course there's a linear term that will account for the a mu d mu phi term as also from the a mu psi bar gamma mu psi. Okay? So now it is a sort of simple matter to take this thing and just expand it out. Okay? And write it out in components and to see what you get. So what do you get? You get the following. You get f bar. That was what we would have had just from phi bar phi. That's not changed. Okay. So we get f bar plus a box a bar plus I del mu psi bar sigma mu psi, okay, plus v mu into half psi bar sigma mu psi plus I by 2 a bar del mu a minus I by 2 del mu a bar a. So that was the term with no v's. This was the term with 1 v, and then there's the term with 2 v's. Okay. So the term with 2 v's is minus I by square root 2. Sorry, this is still the term with 1 v. The term with 2 v's is coming. I by square root 2 a. No, it is the term with 2 v. Sorry, a lambda bar psi bar minus a bar lambda psi plus half into d minus half v mu into a bar. Okay, so first term had it's a bit mixed up. This term is also with one side. Okay, fine. So everything here had 1 v, and this term was also the term with one vector field. This guy had 2 guys because it had an a and a lambda. This guy had 2 guys with a and lambda. This guy had 2 guys with v and mu. So this, if I put up here, this would be no v's, 1 v, and 2 v's. Okay, all good? Which one? V mu. Okay, now are all these terms you expect? You see, this term, at the moment all we've done is just expand. Now we're going to group. So this term, which is this guy, and this guy, together with this guy, make up the standard kinetic term for scalars. Okay, that would be after an integration by parts, would be a d mu a bar d mu a. Right, this is clear. There would be a term with two derivatives, two terms with one derivative and one a, and one term with two a's. That's what we have. Right? On the other hand, this guy, which is the standard kinetic term for psi, combines with this guy, obviously, to become psi bar del slash psi. Right? So what's happened is that the matter field, the scalar part, has become its usual kinetic term with the gauge, with minimal coupling. The fermion part has also become the usual kinetic term with minimal coupling. F is just on its own trip. F bar. You see, F gets life when we add a superpotential. D is the same D that appeared in this expansion. Right? The expansion of V. You're saying which one? So this d mu a bar is just. It's d. No. Sorry. It's the covariators. I'm sorry. It's d mu minus I a mu. I'm sorry. So maybe I'll put these covariant derivatives in yellow. Right? It's not the supersymmetric derivative. It's a bosonic derivative, not a fermionic derivative. The other D's were the alphas. Yeah. Okay. So which terms have we dealt with? We've dealt with this term and this term. We've dealt with this term, this term, this term, and this term. Okay. So what is left? There are two terms that are left. The first term is an interaction which is of Yukawa type. You see the scalar field of the chiral multiplet and the complex conjugate of the spinor and the chiral multiplet together interact with the gaugino. Okay, in some particular manner. Is this clear? So this is a two fermion, one boson interaction, a Yukawa type interaction, and this is forced on you by supersymmetry. So this is a consequence of supersymmetry. In a non-supersymmetric theory with this field content, we could have independently had the kinetic terms of the gauge boson, the kinetic terms of psi, kinetic terms of lambda that we have here, but you could have had whatever Yukawa term you wanted. This is forced on you by supersymmetry. Okay, in particular, it's not consistent to have no Yukawa term. Okay, and the second thing that's important is that you get this D times A by A. Now, why is the second thing important? The second thing is important because, in addition to this, we also have, of course, all I've written down here is the expansion of the gauge invariantized version of this. Okay, there's phi bar e to the power v phi. But we also have d2 theta, w alpha, w alpha. So to this, we need to add what we got from there. Right? Now what we got from there includes the d square. So when we integrate out that d, we're going to get a potential which is sort of, in this case, like a by a, the whole thing square. Phi to the 4 potential. That is also forced on us by supersymmetry. Okay, now some terminology. A potential that comes because we integrate out, these F and D are the symbols that are always used for these two auxiliary fields. A potential that comes about because we integrate out the D in the supermultiplet is called a D term potential. Okay, now, fine. Now, so what we've seen here is that we always get a D term potential when you've got a charged field interacting with with the gauge boson. And of course, in addition to this, we could have turned on a W phi. Okay, we could have turned on a W phi for the chiral bosons. Now this W phi is constrained because it has to be gauge invariant. So if we had just one chiral field with some charge, we could turn on no W phi because any potential we turned on would have some no analytic W phi, no without turning on a phi in the denominator. Okay, because if we turned on like say a phi to the n W phi, that would not be gauge invariant because it would be it's a term of charge n under the gauge transformation. How do we include coupling constant? Okay, very good. So there are many ways. One way would be to just keep track of, let's put an E here. Exactly. Yeah. So if there is E here, suppose this has charge E, we would put an E here, so this would be the gauge transformation. Therefore, to cancel it, we would need an E here. Okay. Therefore, every term that was here would be independent of E. Every term here would have an extra E in it, and this term would also have an extra E. And every term here would come with an E square. Okay, so actually that's a good question, and one of the things we see is that the D-term superpotential is proportional to charge square times phi to the 4, right? Because that's one of the terms that appeared quadratically in that gauge field. Is this clear? Okay, excellent. Excellent. Sorry, so we were talking about the superpotential. If you had just one charge scalar field, one charge chiral field with some charge, you basically don't have the freedom to turn on a superpotential. This is very different from a non-supersymmetric theory. Let's remember this. This is actually a key to many of the constraints we get from supersymmetry. You see, if phi is a complex field of charge 1, then phi star is a complex field of charge -1. So in an ordinary non-supersymmetric theory, given a complex scalar field, we can always make a potential because any function of phi bar is gauge invariant. But the key thing here was that superpotential terms were always d2 theta, that the only additional way of getting potentials for scalar fields, apart from those that you got from the d terms, was through superpotentials. We want zero derivative interactions. The only way of getting that from chiral multiplets is superpotentials. Superpotentials are two integrations over half of superspace. And so the only thing you're allowed to put here to make the Lagrangian supersymmetry is a chiral superfield. Now phi is chiral, phi bar is not chiral, it's anti-chiral. So phi bar cannot be put inside your superpotential. Okay? So the fact that superpotentials are holomorphic. In field space, they're functions only of the complex coordinates, the phis, not of their complex conjugates, the phi bars. Already you're seeing that we get constraints from that. Is this clear? So it's hard to turn on superpotentials if you have very limited field content. Just gauge invariance and d2 theta forbids you from doing that. Is this clear? So if we were dealing with a theory of just one chiral field with one charge, actually in 4 dimensions this would be anomalous. But if we ignore that for a moment, if we were dealing with such a theory, then we would just not be able to turn on any potential, any superpotential, apart from what we've written down here. Okay. If on the other hand you had two fields, let's say phi 1 and phi 2. Phi 1 at charge 1, phi 2 at charge -1. Then you would be able to turn on a superpotential, some function of phi 1, phi 2. Okay? Then you can turn on your favorite superpotential. And then in addition to these potential terms, you would get the F terms, which would be del W by del phi mod square coming from this F. Is this clear? Phi bar square. Right. Phi bar square are additions to the kinetic term. Okay. These are always two derivative terms. So they don't change the potential. These terms always come with derivatives. Okay. The reason is that you always need to do some expansion in do you want to right? It's the same reason that phi bar was a term with derivatives. Okay? So potential terms only come from these superpotentials and these d terms. Other terms are not so controlled, as you point out. Okay? So terms which have derivatives in them are under much less control with n equals 1 supersymmetry. But terms with no derivatives, these potential terms, are under a striking degree of control. Okay? We're going to see how this goes as we go on in a very non-trivial context. Well, suppose I had two chiral superfields. Well, then you can have some superpotentials. Okay? But as you will see, we will be in a situation where you have many chiral superfields. As you will see, when we put all the constraints of the theory together, and you demand chirality, it's extremely constraining. See, the point is that there is a new constraint. Things can only be a function of phi and not phi bar. That may be powerful, may not be powerful. In some situations it's very powerful. Some situations may be less so. But it's a new thing which had no analog in non-supersymmetric theory. Okay, one last comment about this before we proceed. So far what we've written down is just classical Lagrangians. Often, the most interesting questions in a quantum field theory are this. I give you a UV theory, and I want to understand IR physics. Okay? Often the UV theory is trivial, it's free. So when we make these guys non-abelian, that will be the case. Because of asymptotic freedom, in the UV, the theory will be free. Okay? So I give you an almost trivial theory. Okay? In the deep UV, it's just really trivial. Then it initiates an RG flow. We want to know what the endpoint of that RG flow is. Where have we gone? These are some of the most interesting questions in physics. It's the question we ask for QCD. For Yang-Mills theory, right? We take Yang-Mills theory, it's trivial in the UV. What has become the IR? You can answer that, you get $1 million from Clay Foundation. Okay? It's the question they ask for the Hubbard model in condensed matter physics. The Hubbard model is this very simple model which is believed to capture the dynamics of high temperature superconductivity. Very simple model on a lattice. What does it become in the IR? Believe that it captures the physics of strange metals of... There's a paper today by whom? Okay.
This says physics of strange metal and lattice.
Okay, Subin Sachdev has been writing similar titled papers for 20 years. I mean, all of them are great papers. But I mean, I don't think, it's not necessarily what is the connection? Well, one connection goes from via the SYK model. I don't know if you guys are tuned in. Okay, there's this Hubbard model. We won't digress too much, but just for 2 minutes. There's this Hubbard model which, let me see if I can get this. That's right. People draw some sort of phase diagram in this Hubbard model. There are two parameters, T and U, hopping term and potential. And then they draw some sort of phase diagram which, some superconducting dome, some phase here, some phase there, strange metal phase here, high temperature superconductivity here, and so on. Okay, very, very concrete diagram, very concrete theory, but one that has the sign problem, so you cannot put it on a lattice. You cannot easily put on the lattice. Condensed matter physicists, I have no independent assessment of this fact, but condensed matter physicists, many of them strongly seem to believe that this Hubbard model captures the physics of high temperature superconductivity. As you know, physics of high temperature superconductivity is very, very mysterious. Not that much for the superconducting phase itself, but because above the superconducting phase, when you look at these substances, they have these substances are strange metals. They're metals which have very unusual properties. The specific heat behaves as a function of temperature. Now I'll say the power wrong, something like T instead of T squared, or T squared instead of T. It doesn't behave like a Landau metal up to very high temperature, 600, 700 Kelvin. Okay. It's strongly believed that if you understand the physics of the strange metal, then some condensation mechanism will also tell you the physics of the high temperature superconductivity. Okay. Now, question is, how do you figure out the physics of this model? There's something special happening here, and Sachdev himself has basically propounded two kinds of theories. First theory is that if we were at zero temperature, okay, and if you could suppress this superconductivity somehow, and zero temperature, the theory undergoes a phase transition. The thing undergoes a phase transition. And when I was a postdoc or a young professor, lots of talks of this sort, that, okay, now you are interested in the physics here. Your physics may not be exactly where, this is like, okay, this is temperature and this is some T by U parameter. You're interested in the physics here. As long as your temperature is larger than your deviation from the other things, the physics there will be governed by the dynamics of this critical fixed point. Okay? And then just scaling tells you how the specific heat transforms. Okay? So in particular, if it's, okay, whatever. Scaling, just scaling, because it's critical theory, scaling tells you how the specific heat transforms with temperature, and this is it gives you an explanation for the observed behavior. So one theory was that this is controlled by a fixed point here. You're not exactly at the parameter where you've got a fixed point, but if your temperature is large enough, that's the larger scale in the problem than the deviation, the deformation parameter, so it's more or less the fixed point at finite temperature. Then what fixed point, nobody knew at that point, but just the fact that it was a fixed point gave some, and then scaling gives some predictions which seem to be. Another theory that Sachdev had also propounded in early days, but now have got more traction, is that this region is effectively described by SYK type systems. SYK type systems. Now, this is a very funny theory, you might think, because SYK is quantum mechanics. And these theories are like 2 + 1 dimensions. They're thin films. So how does SYK quantum mechanics connect with 2 + 1 dimensional theory? This is somehow a large part of it. The idea is that there's some localization. Things are happening site by site, and each site is behaving almost like quantum mechanics, and then there's some weak interactions. Okay, so it's somehow the physics of disorder and of localization that makes this theory SYK type. Now, both of these points of view had connections to black holes. SYK for the reasons that you guys know better than me, right? I mean, there's a gravity dual theory, or almost gravity dual theory to SYK. The ground state is believed to be described by an extremal black hole. So that's a connection to black holes. And the first kind was because, well, suppose this fixed point here had a gravity dual description through ADS-CFT, then you could get lots of predictions. So this rough idea has been around for a long time. Maybe today's is a breakthrough paper. I don't know. It's a colloquium style paper. Okay. Yes. Okay. Excellent. Sorry. Where were we? Why were we talking about all of this? Okay. Is this clear? We're already beginning to encounter the constraints from supersymmetry on time. Oh, sorry. Yeah, what I was talking about, now I remember. What I was talking about was low energy effective action. A lot of the interesting questions in physics are, I give you a UV theory, and I ask you what is the IR dynamics. Okay? Now, this UV theory may be very special. For instance, we could demand that it's renormalizable. In which case, it takes this very simple form. What about the IR theory? If, one of the questions is what are the true fields in the IR theory? Well, let's say that the fields are the fields that we see. Suppose that's the case. Then we could ask, what is the effective kinetic term for the gauge bosons then? Now notice that the kinetic term for the gauge bosons is an integral over half of superspace. Okay? So the only way that this can be, notice also that W comes with many derivatives. So if we add more W's, if we make W to the 4, okay, that will be higher derivative terms. I'm interested in kinetic term. What can we do to change it? Really what we can do to change it is to multiply this by some function of phi. Whatever function of phi you multiply it would have to be neutral. So if you have just one phi, you won't have any options for what you can do. If you have many phis, you may have some options. Okay? And when you do that, you get some modified kinetic terms. Kinetic terms depending on where you are in this field space of the scalars. Okay? So this is the kind of thing that we could also maybe hope to control, because it's an integral over half of superspace. Okay? This thing, on the other hand, the low energy effective kinetic term for the, where was phi bar phi? Here. The low energy effective kinetic term for the scalar fields, that sounds much harder to control. Because it's not an integral over half of superspace, it's an integral over all of superspace. There are no further constraints qualitatively than what we had classically, than what we had non-supersymmetry. Okay? So in n equals 1 supersymmetry, which is what we're studying now, those terms are very hard to control. Okay? Whereas you might hope to be able to control these terms and certainly superpotentials. Okay? We're going to see this illustrated in examples, in highly non-trivial examples as we go on, but just to give you the basic picture. Any questions or comments about this? Okay. So that's the end of our review of kinematics of abelian theories. We still have to understand how to work with non-abelian theories. Okay? So the generalization of what we've discussed to non-abelian theories is sort of straightforward. Okay? The generalization of what we've discussed to non-abelian theories goes this way. First, our fields phi now transform in some representation of the gauge group as usual. Okay? Our gauge element lambda, okay, is also a matrix in that representation. So if we want, we can be specific and say lambda is equal to lambda A TA, where TA are the representation matrices in that representation. TAR, where R is the representation in which phi transforms. Okay, all good? Now, the first thing we want to do is as follows. Also, our gauge field V. Our gauge field is V is equal to VATA. V is an adjoint field. Okay? T could be in any representation you choose. For the purposes of writing the gauge action, we will choose T to be in the adjoint representation. For the purpose of coupling to matter, we'll choose the representation in which the matter lives. All this is as usual. Okay. Now, the first question we're going to ask is, how does the gauge boson transform under, okay, first question we're going to ask is, how does phi transform under gauge transformations? Okay, and the answer is very simple. It transforms like e to the power lambda times phi. Phi goes to, do we want an I? Did we have an I last time? We had an I, maybe we want an I. Yeah, we want an I. Did we want a minus I? Sorry, yeah, painfully enough, he's got a minus I. I'm going to follow his notation. I'm really sorry if I've messed up with some minus signs. wants, this is how, so let me write an explicit expression. Phi prime is equal to e to the power minus I lambda times phi. This is how my chiral multiplet is going to transform, where lambda is a chiral superfield that is also a matrix in representation space acting on phi. All good? Now, we want to retain the form of this interaction. We want an interaction term to be phi. Okay, so then phi bar will go like, phi bar prime will be equal to e to the power I will be, so phi phi bar prime will be phi bar times e to the power I lambda. Right, is this right? Right, for the usual reasons. We do. This phi is a collection of superfields, correct. Phi is a column. Each element in that column is a superfield. Okay? Lambda bar, thank you. Lambda bar. Yes. Okay, great. And now we want this interaction, e to the power v phi. We want this interaction to continue to capture, to be gauge invariant. And so we need 7.6. Yeah, but it doesn't have to add up, right? Because it just yeah. So, oh, you mean yeah. So we need to know what is the transformation of V. Right. So what we want is that the gauge transformation of V will be the non-abelian version. So it will be e to the power V prime is equal to e to the power minus I lambda bar e to the power V e to the power I lambda. Okay, and then this manifestly does the right thing because they cancel in pairs.
So this is defined through exponential.
Through exponential. Because of course we want a non-abelian transformation. We don't want a linear transformation. Okay, so this is the gauge transformation rule of the gauge boson. Okay, now once again you can take that gauge transformation rule and expand it out. Okay, e to the power v prime is equal to 1 plus inverse Sumino gauge 1 plus v prime squared by 2. E to the power v is 1. So it's not a very complicated gauge transformation rule. Okay, and if you expand it out in components, you will recover the usual gauge transformation rule for the gauge boson. You see in particular that there's nothing more than it's not a terribly complicated rule. Okay, excellent. So we've understood how to make the theory gauge invariant, and we've understood how to make these interactions continue to work. The last thing we have to do is to understand what is the analog of this W. Okay, so the analog of W is as follows. W, which earlier was minus 1/4 d bar squared d, now W becomes alpha is equal to minus 1/4 d bar e to the power minus v d alpha v d alpha e to the power. Okay, now why did we have this funny W? We have this funny W because we wanted W to be gauge covariant, right? Because W is like the field strength. So we wanted to transform nicely under gauge transformations. So we wanted W we want W to satisfy the following gauge transformation property. We want W prime alpha to be equal to e to the power minus I lambda, W alpha e to the power I lambda. This is what we want. Okay. Now claim this this thing does it here. Okay. Let's try to understand why this does it. Okay. So let's look at the gauge transformation of this W. We have W alpha prime is equal to minus 1/4 d bar, and now we've got this e to the power minus v. So it's like the inverse. So we just take inverse of both sides of this. So we get this inverse, so e to the power minus I lambda, e to the power minus v, e to the power I lambda bar. Okay. Then we have d alpha of e to the power minus I lambda bar, e to the power v, e to the power I lambda. Okay. And we want to see how this guy transforms.
Why you change this into power minus v transforms?
Which one?
For e to the power minus v, why you don't?
Well, we know how e to the power v transforms
E to the power minus v
is inverse of this. Okay, so take this is the inverse matrix. So I just took inverse on both sides. Okay, so I got inverse here, I got inverse here, and I got inverse here. Okay, and now how do we manipulate? Now how do we manipulate this? What? Sorry? Lambda is a chiral multiplet and lambda bar is an anti-chiral multiplet. So D on the first guy is 0. And so this D goes through here. So that's the first thing. So this is minus 1/4 d bar e to the power minus I lambda e to the power minus v. And then we get d alpha of e to the power v e to the power I lambda. Sorry? E to the power I lambda goes through d bar. Yes, this e to the power I lambda goes through with d bar. So this is equal to e to the power I lambda into minus 1/4 d bar of e to the power minus v d alpha e to the power v. We're going to use that these two are inverses soon. Right. So e to the power I lambda. Okay, very good. Now all that remains, all that we need is, we wanted this, and the problem was that this was this. Yeah. Wait, what minus sign?
The first one has e to the minus I lambda.
This had e to the power minus I lambda. E to the power minus I lambda. Thank you. Yeah, that's e to the power minus I lambda. Yeah, we want to check that it behaves like this. So we've already got the e to the power minus I lambda out here. We need an e to the power I lambda out here. So now let's check just one more thing left.
We are acting on e to the power I lambda is 0.
It's chiral. It's not the d bar would be 0, and there is this additional. It looks like exactly what we want. Yeah, this extra term is the only one that's bothering us, right? Okay, so one term is what we want when this guy hits this. And then there's this extra term. Have I messed up? Just a minute. One minute, sorry, 1 minute. It kills it? Ah, maybe you're right. Maybe you're right. Maybe you're right. Okay, good. So, good. So we have e to the power minus lambda. So we get e to the power I lambda minus 1 by 4 d bar e to the power minus v d bar e to the power v. That's one term. Plus the second term, as Anurag said, simplifies a bit because this is e to the power I lambda minus 1 by 4. D bar, and then d alpha e to the power I lambda. Give me 1 minute more. Something obvious, yeah. It's not true that in general that d bar d is 0, because for the abelian case that was what W was, right? It's not always 0. Am I messing up some? Let me come back. I'll clear up this algebra next class. Certainly true. These guys claim it's true. Yeah, this is very. Give me 1 minute. It's very stupid. Okay. Wait. It should be something stupid. Have I done it right? Have I messed up? This looks okay. Then I took this through, that looked okay. This killed, that looked okay. This guy went out, that looked okay. All that remains is this guy. What's the deal? Okay, I'll check it and tell you next time. Diksha knows. But it's not enough that it's total derivative because we want W alpha. Yeah. So we want it to be, we want this to be true without any total derivatives. I'm sorry, I'm embarrassed. I can't see why the algebra works. Weissenberger tells us it does, and I know I've checked it before, so it does work. I'll tell you how I messed up next time. Sorry about this. Okay, but if you believe this thing that we weren't able to check, then this Lagrangian trace W alpha now becomes gauge invariant because each W transforms like that. Then those guys go out to the ends, and because trace is cyclic, this thing is gauge invariant. Okay, so So the kinetic term for the gauge boson is this trace W alpha up to this embarrassing stupidity, which I'll clear up next time. We've managed to find, we've managed to write down the non-abelian gauge field, non-abelian gauge theory, trace W alpha plus standard kinetic term for the gauge bosons, but with an e to the, standard kinetic term for the chiral fields, but with an e to the power v in the middle, and any superpotential that you can write down. Okay, so this is our most general Lagrangian, and it's guaranteed to be supersymmetric up to the stupidity that I'll clear up next time. Here, we want trace W alpha. And for the gauge bosons in the phi bar phi, there's contraction of indices, as usual. For the chiral fields, there's contraction of indices, as usual. Okay, so this is our, this is the end of the kinematics of these gauge theories. Of course, anyone who wants more, more.
Is it true that this can happen that d bar p anti-commutator is p?
Okay. Yes.
And d bar p commutator is 0?
You're giving me an argument that d bar d of anything is 0. But we know that for a U1 theory, W alpha is d bar d. So it's not always 0. We computed it. I've done something stupid at some earlier stage, I think. I mean, at this stage, it just doesn't look like it's.
If we take V to be 0, for example, then that statement will say valid.
What statement looks valid?
The transformation of W prime alpha. Basically, W prime alpha will go to W prime alpha. W alpha goes to W alpha 1 because it was.
Yes, you're saying it's consistent. There's a consistency check.
No, not in here.
Uh-huh.
The first equation.
In the first equation, yes.
Take V to be 0.
Yeah, then you say you get 0 here, for instance. No, no, not here.
V to be 0, but
Yeah, you're saying if I take V to be 0, I should get.
the first equation is correct, right?
Yeah, the first equation is correct. I think looks correct. I don't know what I missed. Let me see if they said something here just now.
I think the difference is that d bar d acting on the U1 field is non-zero because that's not a chiral. It's a chiral. Now d bar.
Maybe you're right. Maybe you're right. Maybe this is just identically 0. You want to let's check that. Thank you. Very nice argument also. Schumann's given a great argument. Yeah, Schumann's argument was, I think Chintan was saying something similar also and I dismissed it. Thank you all of you. Okay, the argument was this. There was d bar alpha dot, let's say, and d beta. Okay, so the argument went that this is d bar alpha dot, and then we'll take this through. Okay, so this is d beta d bar alpha dot. Okay, but this part, because it's acting on a chiral superfield, gives 0. Okay, thank you. Okay, now what remains then is the anti-commutator. But the anti-commutator is d bar alpha dot p alpha dot beta on chiral superfield. But Schumann's point was that this d bar commutes with the p. So when it hits the chiral superfield, it gives you 0. Thank you, Shuman, Chintan, Diksha. What? You checked the book. Okay, no, it's a very good argument. As you say, the key point here is that it's acting on a chiral superfield. Okay, so d bar d acting on a chiral superfield is 0, so this part is 0, and therefore we have the result we want. Wonderful, thank you. Excellent. Excellent. Okay, so we're all good. There are two things I want to add before we start doing some physics. If we take this Lagrangian here, okay, if we take this Lagrangian here and open it out, okay, it's interesting to see what kind of terms we get, just like it was for the U1 case. Okay, and I'm going to write down this thing. So what I'm going to do is to take this Lagrangian, which is trace W alpha plus W alpha bar dot W alpha bar dot, okay, plus phi bar e to the power v phi. Okay, so it's the analog of the Lagrangian we had for the U1 case, kinetic term for the matter field and kinetic term for the gauge field. So far ignoring all superpotential terms. Okay, so we're going to get an answer that's sort of very similar to what we got for the U1 theory. Okay, we're going to get an answer that's very similar to what we got for the U1 theory, but let me write it down so that we can look at it. So first we get this, which is now let us allow for the possibility that there are many different gauge fields. Oh, okay. Let me let me write down the no, just one gauge group, but I'll write down the A indices explicitly. So F mu nu A, F mu nu A. This is dA dA, and this D is itself an adjoint field, and it's summed over all these labels, right? I'll write down the adjoint indices even for lambda. Okay, then there is minus d mu A bar d mu A minus I psi bar should be, no, because now lambda is an adjoint field. Okay, so earlier it was uncharged. That's why its derivative was normal. But now we're looking at a non-abelian group. Okay? So now this d mu will be a covariant derivative on lambda, yeah, with a in adjoint. So involving a commutator lambda. Okay? So this is the ordinary f mu nu, f mu nu. This is the kinetic term for the gaugino. But as Diksha pointed out, it's not neutral anymore. It's an adjoint, so it's charged, so it has this kinetic term. Then there is this term from the auxiliary d-type field, this dA term. Okay? This dA term will be our main focus, but let's look at everything else first. Then there are the scalars from the chiral multiplet. There are the fermions from the chiral multiplet. They have their usual kinetic term, but now promoted with covariant derivative. This is the usual kinetic term, but promoted covariant derivative. Then there is the F term, the auxiliary field for the scalars. Okay. Now, in addition, there are the Yukawa terms. Now, let's look a little bit at the Yukawa terms. The Yukawa terms here have a bar Ta psi. This quantity is an adjoint object. Right? This Ta acts on the space of the scalars, and then the adjoint index contracts with the adjoint index of lambda. Okay. Similarly, here we have lambda by a Ta a gives you an adjoint quantity, which lambda a. What?
Just a bar times psi.
What? Sorry.
A bar times psi will be adjoint and lambda a will be.
Well, this T here is in the representation space on these scalar fields. Okay, so this object gives us an adjoint object in the eighth component of an adjoint object. Okay, and then it contracts with here. And what? A and psi are in the same representation because they're in the same supermultiplet.
This is like column R.
Yes. A and psi in some representation. Lambda is always adjoint. Right? And here we want basically this should be an A Ta psi bar. Okay? Good. A bar Ta psi is like a particular adjoint component. A bar Ta psi will transform under rotations like an adjoint index. Right? Lambda A transforms under rotations like an adjoint index, so the dot product is gauge invariant. Similarly here. Okay? So this is the structure of the Yukawa terms. It gets a little more complicated because the gauge bosons. Fine. One interesting thing here is this guy. The D term goes in a way that was sort of similar to what we looked at. There's the adjoint index dA, and then there's A bar TA. Okay? So once again, it's nice and gauge invariant. Now, if we integrate out the D term, what are we going to get? What we're going to get is.
So can you once say that what is the concept of dA and how dA looks like? It has an A index, but other than A.
TA, sorry, which one?
dA. This is dA.
dA. dA is a scalar. It's a field.
Okay.
It's just so. What is D?
A runs from 1 to n, and then there is
A runs from 1 to number of generators. In SU2, A would run from 1 to 3.
1 to 3, and everyone is a scalar.
It's a scalar, right? It came from the, we don't have it here anymore, but there. It was this term. So we will make the expansion that VA, all of these now have an A. Okay? So now when we integrate these guys out, once again we're just completing the square. So what we're going to get is something which is like A bar Ta A, the whole thing square. Okay? So the D term takes this form. This fact is going to be very important for us. Okay? This is the generalization of the fact that Chintan sort of alerted us to. You remember that in the U1 theory, we had phi bar phi, or A bar A, the whole thing squared, times charge square. the E square. Okay? This is like the analog of that. This TA is like the charge. So it's the charge square. Okay? Excellent. So this is the structure of these theories. Okay? All we've done so far is kinematics. Right? All we've learned is how to write down a UV theory that will be supersymmetric. Now the next question is, if we study any of these theories, how much can we actually say about these theories? Okay? So that's the question we're going to address. So let me tell you what question we're going to address. So in the next 3 or 4 lectures, we're going to address the following question. We're going to pick a particular gauge group. Our gauge group will be SUN. Okay. Then we're going to pick particular matter content. Okay. And our matter will consist of the following. We will have NF chiral multiplets in the fundamental. So phi I and we will also have NF chiral multiplets in the anti-fundamental. Okay? Of course, the field content will include the complex conjugates of these. So there will be the anti-chiral multiplets phi I bar, which is in the anti-fundamental. NF, and this is a fund, and this is an anti-fund. Okay. Now, some of you may be wondering, we're in 4 dimensions, as you remember. Some of you may be wondering why, okay, it's nice to have a parameter, so it's nice to have NF quarks, but why can't we do something simpler? Why can't we just have fundamentals rather than fundamentals and anti-fundamentals? Okay? And the answer to this question is simply that the theory would not be well defined if we did not have as many fundamentals as anti-fundamentals, because the theory is anomalous. If you compute the gauge anomaly, and we're going to be doing such computations as we go along, if you compute del mu, you compute the anomaly of the anomaly of the actual gauge group. Okay? Unless you have as many fundamentals as anti-fundamentals, you will find that gauge group is anomalous. It's worse than the chiral anomaly, because it's a gauge anomaly. The gauge theory, gauge invariance would become anomalous in this theory. For the gauge symmetry to remain non-anomalous, okay, we need this matter content. We will be seeing how this. I will write down anomaly equations as we go on. Right now, in the next 10-20 minutes, I'm just going to set the tone for what we're going to be doing. Then we will start it in detail. Okay. For this reason, we are forced to look at theories with as many fundamentals as anti-fundamentals, just to have a theory that makes sense. Okay, the theory without just doesn't make sense. Okay, question we're going to ask is the following. This theory is well defined in the UV. What is its IR physics? Okay, so in the next, this is the definition of the theory. It's the Lagrangian theory. It's what happens in the UV. Question we're going to ask is, okay, at some points we may also allow for masses in these theories. That is, we may also allow the superpotential to be deformed such that W is equal to Mi phi I phi tilde I. This is possible because phi and phi tilde are both chiral. Okay, and it's gauge invariant because one's fundamental, one's anti-fundamental. Okay, so on occasion we will take this theory deformed by these mass terms. Okay, and question we're going to ask is what is the UV dynamics of this theory? Okay, in fact, the most general mass matrix we will allow is Mij. What? What is the IR dynamics of this deformation? Well, it will give each of these fields a mass. Okay, roughly the way of saying that is the following. You remember what the potential is that comes from an F term? It was del W by del phi I mod square, sum over I. Okay, so let's work it out for this. Let's work it out first for the diagonal guy. It's very similar. It would give an off diagonal mass otherwise, but let me just to make the point clear. Okay, then what we get is phi I phi tilde I mi square from the potential, right? And so this is the mass term. Okay, of course this is a mass term in the UV. What effect it has in the IR, that is something we have to determine, but roughly speaking it's a mass. Okay, so this is our theory. This is the theory we want to start with. Question is what happens in the IR. Okay, now before we even ask this question, we should ask ourselves, what exactly do we want to know? Okay, are we looking for some detailed information, or are we looking for some qualitative information? Okay. Now, you see, suppose you've got some gauge theory. Okay, a qualitatively interesting question is this. Okay, a qualitatively interesting question is this: are gauge bosons asymptotic states in the theory or not? Okay, theories are massless gauge boson. Are massless gauge bosons asymptotic states in the theories? Can they scatter? Can they go off to infinity? Stable, exactly. Yeah. You know, at short distances you might see some partons, but that's not what we're asking. We're asking go far away to infinity. Are massless gauge bosons things that propagate out to infinity or not? Okay? In QED, we know the answer to this question is yes. Massless gauge bosons, namely the photon, are excitations that propagate out to infinity. They scatter, we see them, and that's why we see. Right? Okay? On the other hand, in QCD, we believe that the answer to this question is no. Okay? So, a qualitatively interesting question in this theory is this one. Does this theory, in any sense, have massless gauge bosons? Okay. Now there are two ways in which the theory can have massless gauge bosons. So a theory without massless gauge bosons, we will call either Higgsed or confined according to your point of view. Okay, there are two ways of giving gauge bosons a mass, or effectively removing massless gauge bosons from the spectrum. One way is the Higgs mechanism. The second way is confinement. And in simple theories, there is no invariant distinction between Higgs and confinement in theories with fundamental matter. All this we will study as we go along. Are you familiar with the statement? This lack of, you know this, yes. Okay, all this we will study as we go along. Okay, so but anyway, this is a question. The question is, do you have these massless gauge bosons in the theory or not? Now, if you have massless gauge bosons, there are two ways in which they could exist. They could exist in the IR as free massless gauge bosons. Okay? Or they could exist in the IR as coupled massless gauge bosons. Now, a theory in which these gauge bosons are free, an example of such a theory would be, for instance, take 5-dimensional Yang-Mills theory. In 5 dimensions, the gauge coupling for Yang-Mills theory is 1 over g squared f mu nu f mu nu. Okay, this is d5x. This guy is sort of dimension 4. Okay, it's d5x. So g squared has dimension length. Okay, so the true coupling of the theory is g squared times e. That's dimensionless. So at very low energies, the effective coupling is 0. So 5 or 6 dimensional Yang-Mills theory at very low energies is always very weakly coupled, and the gauge bosons are effectively free. Now, it could be that dynamics is such that in 4 dimensions also the gauge bosons become effectively free at very long distances. This freedom won't come through power law, but might come through some RG running, some logarithmic freedom. Okay? And we know that this is effectively the kind of thing that happens in U1 theories. Right? You take QED in just in ordinary 4 dimensions. You take a U1 gauge boson coupled to a fermion. Let's say the fermion is massless. The running of the gauge coupling is that it tends towards being free in the IR. Go all the way to the IR, the coupling goes to 0. So this is the kind of thing that could happen. So option 1 is that you could get massless gauge bosons that are free. Whenever we have, so this is one phase that we will look for. A theory which is IR free and its excitations include these gauge bosons. Yeah, this is one thing we will look for. Another thing we will look for is a theory in which there are gauge bosons in some sense, but they're not free in the IR. Now, the way this can happen is if you get a conformal field theory, something like n equals 4 Yang-Mills theory. N equals 4 Yang-Mills theory at all energies is the same. Low energies, high energies, same thing. And its excitations include gauge bosons. Now, the sense in which it includes gauge bosons is a bit unclear, because these gauge bosons are not scattering states, because in a conformal field theory, there are no scattering states. But they're as much scattering states as anything else. So a theory that becomes conformal in the IR, where the degrees of freedom include, roughly speaking, these gauge bosons, okay, is another possibility. So another possibility is a phase which is conformal in the infrared. And the final possibility is a phase which we can colloquially think of as a confined phase. A phase in which the only degrees of freedom are sort of like glue balls or mesons. Okay? So the question we're going to address, and you will see how we answer this. Okay? The question we're going to address is, in the infrared, which of these possibilities, or maybe there's a fourth possibility, which of these possibilities, maybe some fourth possibility comes about, are we going to actually achieve? Okay? So the question is very clear. We've written down the theory. It's well defined in the UV. We just want to know what happens in the IR. Okay. Now, all of you already, let's try to see if we can get some intuition for what we should expect without actually starting to study the question. Okay? So suppose we were doing not the supersymmetric theory. Suppose we were doing not the supersymmetric theory, but the theory of SUN gauge fields with fundamental, as many fundamental and anti-fundamental quarks. So NF fundamental and anti-fundamental quarks, and SUN gauge fields, non-supersymmetric. Okay? What do we know about this theory? Well, all of you know the following. And in later classes for the supersymmetric cases, I'll be writing formulas for what I'm saying now. But all of you know that the beta function is such that all of you know that the beta function is such that the gauge coupling goes to infinity. So first let's switch off the quarks, no quarks. The gauge coupling goes to infinity in the IR. And gauge theory becomes strongly coupled in the IR. Okay, and in this theory, the theory with no quarks, we believe the theory is confined. Right? There's no sense in which there are gauge bosons. All the excitations are mesons, and well, not even mesons, no quarks, glue balls. Okay, so this is one limit. Now, all of you have also seen the coefficient of this beta function. Right? This coefficient of this beta function, the term that makes it go to infinity, if we compute it at one loop, now I don't know the numbers offhand, but we will get n minus some number times nf. Okay? So the thing that drives it to stronger and stronger coupling at low energies has a coefficient, and that coefficient has n minus some number times nf. Now, why is it n minus some number times nf? That's very easy to see. The gauge bosons are n square number. Okay? And therefore, their effect on the beta function, wherever it is, will be multiplied by n square. Maybe n square minus 1, we're not distinguishing at the moment. Whereas the matter fields are n in number, but there are nf of them. So you should get n square minus n times nf. And I've taken that factor of n out overall. Okay, so there will be some, it depends on what you compute. But the important point is this n minus number times nf. And all of you also know that because of this fact, there is a point where you can make the number of fundamental fields large enough, number of fundamental fermions large enough, so that the beta function turns around. Now in this case, the theory is not well defined in the UV. Okay, so there is, for nf greater than some number times n, theory is IR free. But the theory in the UV, it's not clear what it means. Okay? So in this case, there is no question. There's not a clear question, because there's not a clearly well-defined question in the UV. But there's a very clear answer. If you can get any theory that has a well-defined UV fixed point, that in some intermediate scale flows to this theory, and you want to know what the physics of that theory will be at the deep IR, it's very clear. It will be just a theory of free gluons and quarks. Okay? So you see that for nf greater than n, while there's no very clearly defined question, if you could make that question precise in some context, for instance by finding some UV completion of this thing, there is a very clear answer. The answer is we get free gluons and quarks. Okay? So this is an example of one of the phases I was talking about, where you have free gluons. Okay. Can the sign of a beta function, so suppose we have, so let's see what that would mean. Yeah, so it would be like this, right? Some fixed point at finite coupling. That would change the sign. Yes, so this happens, for instance, in the epsilon expansion for phi to the 4th theory. Yes. So when the sign changes, at the point that it changes, it's 0. So you have a fixed point. Okay, excellent. Okay, great. So we've seen two limits. Limit 1 is nf is 0, where we expect very strongly coupled confining dynamics. Limit 2 is nf is greater than this number times whatever, this number times n, in which we expect very free dynamics in the IR if we can make sense of this. Now, next question you could ask is the following. Suppose nf and n are both large, and NF was just smaller than this number times n. Now what do you expect? Okay? So now it's sort of interesting. Okay. Now it's sort of interesting for the following reason. If you look at the beta function of Yang-Mills theory, if you look at the beta function of Yang-Mills theory in this context, this one loop term, because we're below the bound, is driving you to strong coupling. However, if you study the two loop term, that drives you towards weak coupling in the IR. Okay? So the beta function is schematically like this: dg by d log lambda is equal to, now let's say that by change in scale we mean going towards the IR, which is the opposite of the usual convention in high energy physics, but it's a nicer convention because this is often usually the question we're asking: what happens in the IR? Okay, so what we got here is, let's say, n squared minus number times nf, so it's becoming positive, times g squared. This is the structure of the beta function. And when you compute the second term, it's also of order n square. Depends on the number of gauge bosons and so on, the NF also. But you know, we're very near NF being equal to n. So NF times n is also order n square. Okay? The important thing is that this number here is negative. It's minus times something. Okay? Now, when this happens, what does this beta function look like? This beta function is trying to drive you positive. So it's trying to drive you positive here, but there's a very small number behind here compared to this number. Okay? So that positivity is soon balanced by this negative thing here. And so you get a flow which is exactly like what Diksha was asking. You get the flow driven to this fixed point and then driven this way from the other side. Okay? Now, this stabilizes at a very small value of g. That smallness is controlled by this epsilon. So suppose n minus nf number is equal to epsilon times n. You see that the value of this will be controlled by, this was g cube, sorry. The value of this will be controlled by that epsilon, because when you balance these two terms, there's an extra factor of g here which will balance this extra factor of epsilon. Okay? So what we're going to get is that this thing here is controlled by, the strength of the coupling constant is controlled by this epsilon. And because of that, when you do this more seriously, you can show that at this fixed point, all the g to the 4 and g to the 5 and g to the 6 terms are negligible because they're higher order in g.
But they are not higher order in n.
No, when you do this carefully, really I should do this, actually if you're doing this, this analysis is done for lambda, the TIFR coupling, and all the n's work out, so those terms are really higher and higher order in lambda. Yeah, so the true coupling is weakly coupled at that point. We will see all this in formulas as we go on. Okay? Okay? So, with doing very little work, we have reliably, in this case, computed the IR dynamics of QCD when n is large and nf is large, and nf minus this n is very small. It's very near that edge. What we've got is a UV fixed, is a prediction that the low energy dynamics should be governed by a conformal field theory, and a conformal field theory that is very weakly coupled. And this we believe is true without any supersymmetry. It's just true of Yang-Mills theory coupled to quarks in the real world. So if you take too many quarks, you get IR-free behavior. You lessen that a little bit, at least when n is large. And we expect we get conformal behavior. But you make that even less, and we expect from our experience in the real world, we get confining type behavior. So in QCD, ordinary QCD without supersymmetry, there are three possibilities that seem very likely to be realized as we change number of flavors, at least when n is large enough. As we increase the number of flavors, it feels like we should go from confinement to conformal behavior to free IR behavior. Okay? Now, it's one thing to say this is what it feels like, but what can we reliably say? Actually, the only thing we can reliably say in this whole story is what I said about the free IR behavior and this fixed point. This fixed point has a name, it's called the Banks-Zaks fixed point. And this we can compute reliably. So this part is not conjecture, it's true. Okay? But what happens at smaller and smaller values of NF? There we just don't know because the theory is not weakly coupled. Okay, and as I said, if you actually at small n could show that Yang-Mills was confining, you get $1 million. So the basic picture is this. Number of fermions as that increases makes the theory more weakly coupled. When we go to that weakly coupled end, we can say something about it even without supersymmetry. As we decrease the number of fermions, it becomes more strongly coupled. We get phenomena as hard to get quantitative control over as confinement. Okay? And in real world QCD or just non-supersymmetric QCD with this, while this is what we expect to happen, there are no proofs and there are no certainties. For instance, if n is equal to 3, SU3 QCD, is there ever are there a number of fermions in which the theory goes conformal or not? Now there are no small numbers in the game. It's not sure, not clear. People have opinions, but it's not sure. Right? Okay. So now you get the context. You see this.
So you are taking this n as large. These are for this real thing you said it's n is equal to 3.
N is equal to 3.
So then this epsilon and all.
There's no epsilon. You know, I can't remember how many fermions we would need to 11 some number. We need some number, but it's not, you know, it'll be some number of order 1. So there are no epsilons. You change that by 1, it's not a small number. Okay? So this is we have this general framework in mind for ordinary non-supersymmetric theories, but we don't really know. We can't say anything precise. Question, in this supersymmetric model, can we make precise statements? Okay? Is it true that we get conformal theories? You know, at finite values of n. Is it true that as the number of quarks becomes smaller and smaller, eventually those conformal theories go away and then we get confining dynamics? What can we say about the confining dynamics? You know, can we make precise statements in the supersymmetric theory? Okay? You see, this is, in my opinion, fantastic use of our kind of theoretical physics. There's a question that we really would like to know the answer to, but we can't answer. So what we do is to look at a cousin of that question, which has many of the same elements as the original question. But this is a question we can answer. Now, how much it teaches you about the original question, that you can discuss. But somehow this is what physicists do when they're doing really good work, right? And I think it's a great question. One last thing before we proceed to the actual computations. The question that we are asking and the question that we really wanted to answer. Let's say the question we really wanted to answer was ordinary non-supersymmetric QCD. Okay? The question that we're asking here, we could ask how different is this question from the question we really wanted to answer. And it's different in really one important way. So let's look at the field content of the theory that we have compared to the field content of the theory we wanted. The field content of the theory we have is SUN gauge bosons, SUN adjoint fermions, the gluinos, then fundamental fermions, anti-fundamental fermions, but also fundamental scalars and anti-fundamental scalars. So there are 3 extra fields compared to what we wanted. The fundamental scalars, the anti-fundamental scalars, and the adjoint fermions. Now the adjoint fermions is not such a big deal. If we could solve just pure QCD with some number of fundamental fermions and some number of adjoint fermions, I think we would be pretty, that would already be pretty good. What makes the theory quite different is the scalars. Okay? And the reason the scalars make the theory different is that, as you will see, the scalars can give a moduli space. You know, fermions are just fermions, but scalars, in the absence of a potential, can go very far. And it's the scalars that is really the irritating thing. It's the real difference between the model we want to study and the model we can study. Okay? So it's not like we're able to do it without a price. We're able to do it with a price, and the price is that we're going to have to deal with these, that we have these scalars which have no analog in the theory we want to study. Okay? So, okay, these are the caveats. Now, with all this in mind, we're going to undertake the study of the theory we can study and see what we learned. Okay, let's see, shall we start today or is it already 1:30? Okay, next time.